In order to understand why a reaction happens faster or slower, we have to have a knowledge of collision theory. So collision theory is so named because it's the idea that for a reaction to happen, the particles of our reactant, the particles of the substance that we're putting into the reaction, have to actually come into contact and collide. Now, if you have a collision between two particles, they don't always just react. You actually need some energy, otherwise they just bounce off each other. That minimum energy has a name. It's called activation energy. You might have heard of that before. If there's enough energy to reach that energy barrier, we will actually have a reaction. Otherwise, we just get particles bouncing off each other and not reacting. So those are the two requirements that we have in order for a reaction to occur. Now, when we're thinking about reaction rate, this is important because the number of collisions that end up actually in a reaction is proportional to the rate of reaction. So the more of them we have happening, the faster the product is going to be formed and the faster the reactant is going to be used up, which is our definition of faster rate. So if we can cause more collisions between reactants in the same set of time, we will get a faster reaction. If we can give each particle more energy so that it can get over that energy barrier, the initial energy that it needs to react, we can get a faster reaction. And if we can find a way to make it so that the particles require less energy, we're going to get a faster rate of reaction because we're going to end up with more particles reacting. So that our aim here, when we're trying to increase the rate of reaction, is to make as many reactions happen as possible in the shortest possible time. Today we're going to have a look at the number of collisions per second and how we can increase that. Now the most obvious way here is if you have a certain concentration of solution or gas, if you put more particles in and you keep the volume the same, you end up with a higher concentration which has more particles in it, and because there are more particles, there are going to be more collisions. If we increase the concentration of a solution, we increase the number of particles in a set volume, and it's important to make sure that we understand that this is the same volume with more particles, not just throwing more substance in, we're keeping the volume of the solution the same at the same time. We have increased the concentration, we have more particles, that means that more collisions will happen in the same time, and time is really important here. Because we have more collisions happening, the chances of any of these collisions being energetic enough to have a reaction is increased. If you think about it, if 5% of particles react and you increase the concentration so that there are more particles there, then 5% of more particles is going to be a bigger number of particles in the same amount of time. So the reaction rate will go up. Now that's for a solution. If we have a gas, we have exactly the same idea actually. You'll notice that all of the bullet points there are exactly the same. The difference is we don't call it concentration, we call it pressure, and the two are pretty much related, but when we're talking about a gas, it's more usual to think about it as a pressure. But again, same idea. The number of particles in a certain volume is increased, which means the number of collisions that happen is going to increase in a certain time, and therefore the probability of a collision resulting in a reaction is going to increase, and therefore the rate of reaction is going to increase as well. So one more way that we can increase the number of collisions per second would be cutting up our solids. So if we have a solid, if we imagine this is a solid, you can see I've got 20 particles on the outside here. We've got 6 across the top, and then the top one's already been counted, so we've got 5 down each side, and then 16, and then 4 across the bottom, which haven't been counted so far, is 20. So 20 particles around the outside. That means that in order for the ones in the middle to react, the first 20 have got to be used up. And so there are only 20 possible reactions here for this particular lump of solid. Now, if I split it into smaller particles like this, I now have 3 across the top, then 2 down on each side, which haven't been counted so far, which gives me 7, and then 1 at the bottom, which I haven't counted so far around the edge. That gives me 8 particles around the outside of each of these blocks, and we have 4 of the blocks. We have the same mass of substance here, perhaps, the same number of particles. We have 4 of these, so 8 fours are 32. We have increased the number of possible reactions by dividing it up into smaller pieces and keeping the mass the same. And so if we take that to the extreme, every particle here can now react. And you see we've got smaller chunks again. We've got 2 by 2 chunks. There are 4 particles which can react in each one, and there are 9 of them. 4 nines give me 36. So the smaller particles of a material, the higher our surface area to volume ratio is. Now, this is obviously in 2D, but remember that we're talking about 3D here, really. And so we've increased the surface area to volume ratio. So when we're increasing the surface area of a solid, we are increasing the number of particles that can collide at any one time. And therefore, we are increasing the probability of collision resulting in a reaction. And therefore, we're increasing the reaction rate. So I'm going to talk about one more thing which actually doesn't affect the rate of reaction, and that is increasing the amount of reactant. Lots of people put this down as an answer, but it's actually not true to say that it affects the reaction rate per se. Now, obviously, you do get a slightly different rate of reaction at different points of the reaction, but if I just show you 2 plots or 2 sketch graphs of what that might look like, if you had the first line as your original experiment, and then you put more in, you can see that the 2 lines basically start off at the same gradient, and we would say that therefore they start off with the same reaction rate. Now, admittedly, if you look at the how steep the graph is, you can see obviously the one with more has obviously produced more product, and therefore it stays steeper for longer. But initially they were the same gradient, and so therefore it hasn't actually increased the reaction rate per se. It's just there's more stuff there, so it's going to continue reacting for longer, because the reason, or one of the reasons, that these graphs curve over is because as the reaction is going, we're actually using up reactant, and therefore we're reducing the concentration, which we know slows the reaction rate. So the concentration is decreasing faster for the experiment with fewer particles in it, a smaller starting mass, because we're using it up at the same rate initially, and so it's going to be used up quicker, and therefore our concentration is going to decrease faster. And so we know the concentration affects reaction rate. As we use it up, we're going to get that slope of the graph curving around until it's flat when the reaction rate equals 0. Let's compare that with what happens when you have a higher and lower concentration. The faster line here represents a higher concentration, the slower line represents a lower concentration, and you can see that they end at the same height on the graph because they're making the same amount of products at the end. That's what we mean when we say faster reaction rate. You can see at the beginning of the graph here, the gradients are completely different at the start, and that's what we're really talking about when we're saying faster and slower reaction rates. So concentration, pressure, and surface area are the 3 ways that we can increase the number of collisions to make a faster reaction rate.